order to argue about what the runtime of quickselect is, we're going to use a similar argument and figure out how many times do we pick a good pivot, one that kind of evenly partitions our list, just like we did with quicksort. So we're going to define a pivot as being good if it almost evenly breaks up our sequence so that neither one of these L or G lists is more than 3/4 the size of our original sequence. We want them both to be small enough, not exactly half, that's too strict, but no more than 3/4 the size of our original sequence. So this would be a good call. We want to have a call like this, a good pivot. A bad one would be if it unevenly distributes our sequence into L and G, where either L or G is too large, meaning one of them is larger than 3/4 the size of our original input. So this would be not a good pivot. And again, we can argue that we'll pick a good pivot half of the time. We can expect to pick a good pivot half of the time because half of the elements in our sequence will be, as we had defined it this way, a good pivot. And why that's the case is we can count up how many pivots are good if we were to visualize our sequence as already being sorted, just for the purposes of us being able to count how many items are good pivots in this sense. So if we visualize this as being already sorted, again, we can break it up into kind of quadrants here, where we've got a quarter of items in the first quadrant, a quarter of items in the second, third, and fourth quadrants. And for anything in the first quadrant, because these are smaller values, everything to the right will be greater than that pivot if we were to pick any one of these items, which means this would be a bad pivot because our list G would be larger than 3/4 the size of our original input, because everything to the right here, we've got 1, 2, 3 quadrants, all of these items would be larger than our pivot. So this would be a bad pivot for that reason. And similarly, we can say that anything in the far right, the last quadrant, would be bad because all at least 3/4 of elements to the left of it are less than it, which means our list L would be too large. But everything in these two middle quadrants would be good because we have enough items less than and greater than in order to guarantee L and G are large enough. Both of them are large enough, which means neither one of them can possibly be larger than 3/4 of the size of our original sequence, because we'll have at least 1/4 smaller and 1/4 larger. Okay, so we can guarantee that the probability that we pick a good pivot is 1 in 2. So we can use this to our advantage when we look at the expected runtime of quicksort. So in order to argue about the runtime, we're going to use two probabilistic facts. One is that the expected number of coin tosses required in order to get one head is 2. So if we flip a coin 10 times, a fair coin 10 times, we can expect that we would get heads 5 times, for example. And we'll use that expectation as a linear function. So that just means that these two properties hold. We're going to use this because we're going to take the expected running time. So our running time here, we're using T of n to denote this. This is the expected running time of quickselect. So we know that the expected running time is, we can represent this recursively because we make a recursive call to either L or G, but this is no more than the running time of by the time we pick a good call. So we have the expected number of times, the expected number of calls we have to make before it's a good call, and when we do so, we have to partition our sequence. So we have some constant number times however many elements we have. This is how many times we have to partition and how many times we have to do that before we make a good call. But by the time we make a good call, then that means we break up our sequence into, no matter if we recur on L or G, if we made a good call, then that means it's no more than 3/4 the size of our original input, and we call quickselect recursively on that smaller sized input now. So we know from the first fact that the expected number of calls before we get a good one is 2, because we have a 1 in 2 chance of getting a good pivot. Now we can just use iterative substitution and repeatedly apply this formula to now t of 3/4 of n. So we'll apply the same formula to t of 3n over 4. So this is how we get the following. So we've got t of 3n over 4 is less than or equal to t of, we take 3/4 of that input, which is now 3/4 squared of n, because our input was 3/4 of n, plus 2 times b times whatever our input size was, which is 3/4 n, and then we still have this left over 2bn. And we can keep applying this, right? So now for t of 3/4 squared n, we again apply that same formula, and we're left with the following, keeping the same leftover that we had from the above formula. And then we can keep doing this until we establish a pattern. So we're making kind of skipping forward a few steps now that we could repeatedly apply this iterative substitution until we have a constant size input that we're working with. So I'm just going to write this kind of a different way. So we've got 2bn plus, oops, here plus, 2bn plus 2b3/4 n plus 2b3/4 squared n plus, and we can keep writing it this way. And from all of these terms, though, we can factor out our common. We've got 2 times b times n in all of them. So we can factor that out, and we're left with here 1 plus 3/4 plus 3/4 squared plus 3/4 cubed, plus if we were to keep applying this, we would continue to have increasing powers of 3/4. And then from there, we can replace this summation with, we know that this can't exceed 4, and the reason for that is this is a geometric series. Let me refresh. So we have, if we take the sum of the first, we could go to n, but in fact, if we were to go even to infinity, of some number a times some number r, all to the kth power, that this is equal to a times 1 minus r, as long as r is not 1. And we can basically plug this in for when a is equal to 1 and r is equal to 3/4. So this is just taking the first, the summation of all powers of 3/4. So here we have 3/4 to the 0th power, plus 3/4 to the first power, plus 3/4 to the second power, and so forth. So if we plug this in, we're left with this value, this summation, which we don't end up calling this infinitely many times, but even if we were to go up to that amount, this is no more than 4. So our total running time is no more than 8, 2 times 4, 8 times b, which is some constant, times n, which means randomized quick select runs in linear time. This is our average case, that is. So this is the expected running time. Now, one question that we can ask is, we have, actually before we get to that, so we have the expected running time of quick select. This is because we can expect that we're not going to get a bad pivot every single time. So this is our average runtime of randomized quick select. But we still have the worst case running time if we're extremely unfortunate that we happen to pick a bad pivot each time. This could be n squared. Okay. This is just that maybe we want to find the kth smallest element, and we happen to pick the unique minimum or maximum to where our partition is bad each time. But we don't expect that this will happen. If we pick a random pivot, we can expect that we get a linear runtime. So this is our average case. But this is assuming that we're using some element of randomization here, that our pivot is random. And one question that we can ask is, if we can come up with an efficient randomized algorithm, can we also come up with an efficient deterministic algorithm? And for selection, we can. We use the same solution to solve the selection problem as before, but we need a deterministic way to pick a good pivot. Now, if we knew what the median element is, that would definitely be a good pivot. So remember, the median item is if this is a sorted sequence, the median would be just that middle item of a sorted sequence. So this would guarantee that our pivot is excellent, in fact, that we would have kind of half of our list on one side and half of our list on the other side. But the problem with finding this exact median is that this is actually a sub-problem of our selection problem. This is, we want to select the n over 2 smallest item. So we can't exactly use this in order to help us solve the selection problem, because in order to do so we would have to solve the selection problem. So we can't use the median as a pivot, even though that would be an excellent pivot. Even just finding it would be essentially solving the problem that we want to solve. But without finding the median, rather than finding the exact median, we can efficiently find what we'll call the median of medians, which will prove to be a good enough pivot. So it's not the exact median, but this is a median of medians. So how we do this, the main idea is that, so again, we're going to use the same selection algorithm that we saw before, but the only difference here is rather than picking a random pivot, we're going to deterministically get a good enough pivot. This is a median of medians, so this isn't a median exactly, but we'll see that it's good enough for our purposes. And how we find this, which will give us a guaranteed good pivot, but how we find this deterministically is that we'll take our original sequence, so this is our large sequence, and we'll divide it into n over 5 lists, each having 5 elements. So we could just count up, here's the first, second, third, fourth, fifth. That's one list, 1, 2, 3, 4, 5. That's another list, and then just keep counting kind of in increments of 5. And each list will have 5 elements in it, and we'll have a total of n over 5 lists to work with. And for each of these smaller lists, we're going to find a median in that small set. So this is just a constant number of comparisons for each small size list, and we've got n over 5 of them, to figure out which among them, maybe this one is the median, or this one is the median. That would be the third smallest element in this list of 5. And then take all of these smaller items that we've found. Now we've got, here's the n over 5, each one of these items in this list corresponds to one of the medians, baby medians, that we had found of these smaller size lists. So we've got now a list of size n over 5, but all of these items correspond to some median of the n over 5 list that we had here, and then we recur. So we again divide it into smaller sized lists, each of size 5, find the medians of them, and then take a list of only those medians and then recur again. Right? So we're recursively finding the median of these medians of small size lists, these baby medians. And we can guarantee that the median that we're left with, the median of medians, is a good pivot. And the reason for that is we can again use a kind of a counting argument so that we can visualize it and count up how many items are guaranteed going to be less than this median of medians, this element that we find, and how many will be greater than it. That way we can show that there are enough in either list to show that this is a good pivot, that neither L nor G will be too large. And so we're going to visualize this as, let's say, here's the first 5 elements, the second 5 elements, and so forth. Here's our n over 5 lists, each of size 5. And we can order this in such a way that here's the smallest item of this list of 5, and here's the largest item of this list of 5, and we do this for each one of these lists. And then we can also rearrange each of these lists so that they're ordered by their medians here. So these are those medians of medians, or these are a list of all the medians, and this would be the median of those medians. And we can order all of these lists based on the value of these medians. Just again, so that we can count up how many items are less than or greater than the pivot that we end up with. So for example, if this median is larger than this one, then we'll move this entire list over to the right so that we have all lists are ordered by their medians. So we'll have this from smallest median over here to largest median over here. Okay, so now that we've done that, then here's the item that we're going to end up returning. This is that median of medians. Not necessarily the median of our original sequence, but we'll see this is a good enough pivot for us to choose. And the reason for that is we can count how many items are smaller than this pivot. We've got everything on the same line here to the left. Since we had ordered based on medians, each of these medians are smaller than this one. And these two items of the same list are smaller than this one. And in fact, everything in this kind of upper left quadrant is less than or equal to this pivot, because since this pivot here is less than it, and all of these items are less than this pivot, then we can say everything in this upper left quadrant is less than or equal to the pivot that we end up with, this median of medians. So all of these items, at least all of these items, maybe more, but definitely all of these items will be in our list L, less than our pivot. And similarly, we can see that since we've ordered this from smallest to largest based on the medians, that all of these medians are greater than our pivot, and all of these elements in the same sequence are greater than this pivot. And in each of the remaining sequences to the right, these values are greater than this median, which is greater than our pivot. So we've got everything on the right here. This will be at least in our side, the number of elements in G, which is greater than our pivot. Which means that since we can guarantee, for example, that we've got a quarter of elements in L, then that means G can't be larger than 3/4 size. And for the same reason, we can guarantee at least a quarter of items in G, which means we won't have more than 3/4 of elements in L. So we can use this to guarantee this is a guaranteed good pivot because we can show that L and G will be small enough. They won't be more than 3/4 the size of our original input. Now we won't get into seeing the exact runtime of why this deterministic selection algorithm runs in big O of n in the worst case, but you can look at your book for the analysis if you're interested. But the main idea here is that we can solve this in linear time in the worst case, deterministically. So rather than picking a random pivot, we have this kind of complicated way of picking a good pivot, not the median, but a median of medians. Okay, if you have any questions, post on Piazza, let me know.